All right then, welcome everyone. So we previously have done a bunch of the Cryptopals stuff. We've done 1 through 4 on set 1. Just to review. So we've written some helper functions. We're able to convert between hex and base 64 and raw strings, which is quite useful. After that, we implemented a fixed XOR which we're able to take 2 raw strings, XOR them together, come up with an expected result, which again, pretty simple overall. Nothing super challenging yet. And then we started playing with actual ciphers. So first, we needed to find a key and decrypt a given message. Which we just used because this is 1 byte, we're able to walk from 1 to 255. And we built some relatively rudimentary rules, which helped us to determine whether or not a string was likely to be in legible English, with the assumption, of course, that it was going to be in 8-bit ASCII. And then finally, last time, we were able to use all of this code to walk through an entire list of strings and find the single string which was encoded with a single byte XOR cipher. And then we figured out everything else is, I'm going to say garbage. In this context, it was garbage. It may well have been meaningful, but it wasn't meaningful in the context that we were working in. So we were able to find the one that was meaningful, and we were able to sort out, which of those was going to be useful and which wasn't. So far, so good. And so pausing for just a moment, I just realized that I've had the web browser up over the terminal, so that's good. It's good streaming. Multitasking is hard. But still, so to pause for a moment, want to give everybody a chance. I know that some people were going to go back and do it on their own. Just in case there's any questions, I'm going to ramble on for another couple of moments to wait and see if anybody speaks up. The Mass, thank you very much for the Twitch Prime sub. Since I got a totally different crowd from normal today, just as a reminder, all the money that I get from this stream, from subscriptions, from cheers, everything gets passed along to the Extra Life charity drive that's linked in my stream info. So stuff like that makes me feel real good, but also you're making sick kids feel less bad, and that's even cooler. All right, it looks like we are probably good to just start moving on. I don't see any questions popping up in chat quite yet. So, step 5, we're going to be implementing repeating key XOR. So we are going to be given stanza of an important work in the English language, and we're just going to encrypt it under a single key, a key that we have predefined. That. Let me pull up Cryptopals on my primary monitor. Go. We know our expected string as well. We are encrypting with the key. Nice. And we're going to be 2-hexing that. All right. Well, that's a bummer. There we go. I think that last week I was definitely an idiot. XOR single byte makes more sense than single byte XOR, but hey, whatever. This is fine. So we're no longer accepting a byte, we're accepting a key, so let's just go ahead and change that. And for now, just to make sure that everything is aligning properly. All right, so we can see that we are definitely failing, and that's good. We expected to fail. We're not doing anything with the string that we're passed yet. So let's go ahead and going to be just a little bit prettier. That's a lie. That's not even a little bit prettier. It's the spanning 2 lines thing that really sucks. But whatever. We'll work with it. All right. So let's pull open our single byte. So our single byte XOR, we just take a string. We're going to coerce it into an array of bytes. Then we're going to map it where we just XOR the byte versus our key, and then we take the character of that. So the nice thing is we can still do essentially that. So So let me explain what cycle does for anybody who doesn't know what that one is. So cycle's pretty useful. If we take, let's say, an array called 1, 2, 3. We try and take 5 entries from it. We only get that original 1, 2, 3. There's not 5 things in there. But the cycle method on array is going to, or really on any collection in Ruby, is going to take that collection and it's going to cause it, as soon as we hit the end, it's going to wrap around to the beginning again. So this is actually an infinite series of 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So now when we take 5, we get 1, 2, 3, 1, 2, which is roughly what we expect. And it just so happens to be the exact behavior that we want for a repeating key XOR. So now, before we do anything, we're going to say string.bytes.zip key bytes. Now remember, that's going to take each entry in this array of bytes out of this string, and it's going to give it its corresponding matching entry out of the key bytes array. Now this is quite nice because as soon as string terminates, it's going to stop trying to pull from key bytes. It's not going to follow both of them until their logical conclusion, only the first one. So as soon as string ends, key byte stops, being calculated, and we don't end up with just an infinite loop here. And now we can do roughly what we were doing before. We can map. But once we do this, now we know that we're zipped between our character from the string and our key byte. And we can do the exact same thing that we did in the above function. So this one's probably going to work, or maybe it'll blow up. That'll be fun too. All right, well, we got something new, which is good. Double checking here. Yeah, OB is definitely what that should be. Key, str. That looks good. All right, so here, let's figure out what's going on. Let's tap in and we're just going to exit early. I just want to know what my first pair is. Or I can get all of my pairs. 66, 73, that is exactly what we expect. All right, let's drop that and take another look. I could be wrong here, but this looks like I'm getting occasional truncations, which is interesting. Looks like a total of 3 characters have been truncated, which I don't love. All right. But it looks like the very first character was truncated out of my hex string, which is intriguing. So I'm going to go out on a limb here, and I'm going to say we have managed to miss so far, but have finally hit probably a bug in my 2 hex. All right, so I see exactly what I did wrong. Yep, so I'm going to catch up with chat real quick while I sit on the first mistake that went completely uncaught, amazingly enough, in the first 4 exercises. What if the key is longer than the string? Well, that's a really interesting question, math jargon. In the case of a repeating key XOR, you would expect the target string to be longer than the key. In the case where the key itself is longer than the target string, at that point it doesn't really matter. You're only going to take as much of the key as you need. So if the key was, just the numbers 0 through 9, and we were trying to encrypt the message hello, we would just take 0, 1, 2, 3, 4, and that would be it. And that would be what we XOR against hello. And the rest of the key would be completely discarded. All right, so I don't see a ton of people talking in chat. Oh. Welcome in, Kashire. Yeah, I'm glad that you've been having fun. Would the zipping handle that? Absolutely. And while I sit here and have my absolute shame sitting on the screen, I'll show you why. So here's the case where we have our ciphertext hello, or ciphertext, our clear text hello, and our key, which is just 0 through 4, 0 through 9 in total, but for hello, just 0 through 4. You see, we truncate, we stop pulling anything from the zipped collection once we hit the end of our original source. So this is a bug that I'm really surprised we haven't hit yet. Not too terribly hard, though. At this point, or actually, no, that's from hex, but I'm willing to bet that 2 hex is the same. Yeah, just byte, 2 string, 16. So in this case, I'm not doing anything with any byte that has a leading 0. Specifically, I'll show off what's going on that's wrong here. So 0 to string is just 0, that's expected. And 10 to string, it's just A. Again, this is expected. However, we need both of those characters. Both of those characters definitely matter. We want the full, the leading 0 for any of these bytes smaller than 16. So what I'm going to do is I'm just going to say, so this is a syntactic sugar to sprintf. So anybody who's familiar with printf syntax and format strings in general, this probably doesn't look too weird. But what I'm saying here is I've got a escape character, an escape code coming up. Now I gave it a 0, and this 0 matters once we interpret this 2. So this 2 says, I want the resulting string that you give me to be too wide. And the 0 says, fill any blank spaces in with zeros. And then S says, you're going to be working on a string. And I completely lied. Well, neat. Which is fine, because if I just use X instead of S and I never bother coercing to string, we're fine. There we go. So now I think we might have a better shot of getting this one. Cool. Success. So there we go. We were hitting the 16 in 255 chance that we're going to hit a leading 0 in our result text. But just to walk everybody through, just super step by step, what is going on here. We're going to have, I'm going to give us a slightly simpler or clear text here. A little bit shorter. Let's go ahead and pull up our XOR lib so that we can walk through what we want, what we're doing bit by bit. Let's say this is our string. We've got a key, which is going to be hello. That'll actually show off some interesting properties of ways that you can give yourself away with a scheme this simple. So first thing, we assigned key bytes to k.bytes. To key.bytes. But we also gave it a cycle. We said, repeat this forever. Thankfully, it doesn't try and display that, because if it were to try and display what the cycle was, we would be sitting here at the computer until the heat death of the universe. And I don't know about all of you, but I do like occasionally doing fun things like eating and sleeping. So we then took our string, which was hello string, stream friends. We converted it to bytes. So now we've just got the ASCII values of all of those. And then we zipped that up with our key bytes. Now, because key bytes is an infinite cycle, we have sufficient key material to assign a byte to every single one of these pairs. You'll often hear 2 tuples to refer to them. That just means that it's a set of 2 things. Now, again, our key happens to match the first 5 characters of the string. You'll notice that we start with a pair of 72s, 101s, 108s, 108s, and then 111s. For those of you who know your binary algebra, you kind of know where this is going. Now, next up is where really most of the magic happens. We do a map. Now, all that map is it says, I'm going to give you a function, and I want you to apply that function to every element in this list. So the function that we gave it took 2 arguments, which it just happens to extract both of the elements from our 2 tuple. It XOR'd them. The caret in this case is an XOR. And then it converted the result to a character. So now, here's what we're looking at once we have our finished string. And you'll notice the first 5 characters here are all null, which is quite interesting. Recall that an XOR is only going to be 1 if both of, or if one or the other bit is set, but not both. So, since the entire byte is identical, in fact, we'll do 72.2 string, give me in binary. So once we break like the byte for H, capital H down to binary, you know, now we can start kind of visualizing what's going to happen when we have 2 of these and we start XORing just down each single column. We're going to get 0, 0, 0 because they're all the same, 0, 0, 0, 0. So null byte. Anytime that you hit your character and the key, the byte that you're applying, being the same, you're going to end up with a null. But so we got to that point, and then finally we just called join. And join takes an array of strings, and it just squashes them all together into a single string. And then of course after that we said 2 hex, which I didn't include, so we're not going to do that part. But hopefully that's relatively illustrative of what went on for level 5. I'm going to give it a moment, just in case anybody has questions. Yo, Loon, thank you very much for the host. Welcome in, everyone. Little bit different content than normal. On Saturdays, I do some programming, InfoSec related stuff. I'll be doing some speedruns later on, so hang out. If you're interested in cryptanalysis, I'm going over just the first set of the Cryptopals cryptanalysis challenges. So hop on in, ask questions. Welcome. You're new to Ruby. Well, thankfully, a lot of what I'm going through here is stuff that, irrespective of what language you're working in, the concepts are not really going to change. And I'm doing my best to keep the code at the level where, if I was writing this in C, just looking at the Ruby, I would say, all right, well, I've got a string, I need to take bytes from it. All right, I've got all of these key bytes, I need to figure out how to cycle through them over and over again. And now I need to start, you know, taking those and then XORing A versus B across the row. Did I have a look at the Facebook CTF? I have not. I don't have a Facebook, so I wouldn't have heard about it from them. And right now, all of my InfoSec Twitter is talking about Circle CityCon, and I'm not at all filled with FOMO at all. Definitely. Alright, so I'm not seeing a ton of questions. Let's go ahead. I'm going to slowly assert that we'll move on. What is InfoSec? It's short for Information Security. It's just a broader umbrella term for anybody who does, whether it's defensive security, people who work in the SOC, people who, you know, deal with network security, things along those lines, or more on the red team attack focus side. Could someone willing to break the cipher look at the zeros in the encrypted message and figure out the plain text and the key? So figuring out the key is the first step to figuring out the plain text. And you might recall that previously we broke a single byte XOR. That was, I believe, the third challenge, where we had to just walk through every potential byte, and we built some rules out, which are detailed right here. And just based on those rules, we were able to figure, here's the key that was used to encrypt this string, a single key XOR. And here you know, is the resulting clear text. So previously, we had managed to figure out exactly what byte was used to encrypt that clear text. So, to answer your question, yes, that string of null bytes right at the beginning of the string, that's a hint. That gives us an idea. Hey, I wonder if this is related to what type of crypto is being used. It's not random, or it's certainly not random appearing. Of course, you know, true randomness means that you will eventually get an infinite series of zeros or an infinite series of ones and so on. But realistically, we expect a certain amount of entropy across the string for a well-functioning cryptographic function. Because it's very, very not random, because there's very low entropy in that string of null bytes, that gives us a hint that, hey, maybe somebody used something that's really primitive, and maybe we can start looking at this. Maybe it's some sort of weird Caesar cipher, and that's indicative of the key. Maybe it's, you know, Veneer cipher. Maybe, you know, somebody just took the string, reversed it, and then used that as an XOR. There's a ton of things that could be going. What terminal is this? I am using console under KDE Plasma. And then tmux under that, because tmux. But that's a really good question, and that's one of those questions that you ask that, and that's what gets all the wheels turning, that makes you start looking at, you know, series of bytes and going, I wonder if that could be something that was encrypted in a more naive method, and a repeating byte XOR is definitely a very naive cipher. But yeah, good question. I'll give just another moment, just in case anybody has any follow-up, and then we'll move on to problem number 6. All right, cool beans. Challenge 6, breaking repeating key XOR. So very, very apt, given that question that was just asked by, oh man, I'm going to screw this one up, and I apologize in advance. I'm going to guess Nasha Svobodnoye? My Russian is terrible. I can kind of read Cyrillic. My ability to pronounce anything in Russian or related languages is worse than terrible. So I apologize. I apologize to anybody who speaks Russian for having to hear that. But to move on before I think about how bad that was, let's look at challenge 6. So we're going to break repeating key XOR. So we've got a file. I'll download it in a moment. It's been base 64'd after being encrypted with repeating key XOR. We're going to decrypt it. So we'll go over the steps now. I've got the sidebar is going to continue with all the stuff that we're doing step by step. So we're going to have a key size. It's a guessed length of our key. We're going to go with 2 to 40 because they say so. Going to write a function to compute the edit or Hamming distance between two strings. So the Hamming distance between two strings is the number of bits that are different between them. For each key size, we'll take the first key size worth of bytes and the second key size. We'll find the edit distance between them. Then we normalize that result by dividing by key size. So then the key size with the smallest normalized edit distance is probably the key. So we could proceed perhaps with the smallest 2 to 3 key size values, take 4 key size blocks instead of 2, average the distances. So after that, we probably know the key size. We're then going to break the ciphertext into blocks of key size length. Then we transpose the blocks. Make a block that is the first byte of every block that is second byte, and so on. And then we solve each block independently as if it was a repeating character XOR. We already wrote the code to do this, as we've looked at. And then we rebuild the string. So this is the first, like, real cryptanalysis problem that we've done, that we're going to be doing. Like, single key XOR, that, you know, it's not impossible that you'll run into it, and especially if somebody doesn't care about secrecy, really, they just want to make it so that people can't, you know, immediately read something at a glance. They might use something like that, but it's a toy. Breaking repeating key XOR is the first real thing that we're going to do. It is conceptually not substantially different from breaking a Caesar cipher. And I would strongly recommend anybody who's interested in this topic, like, go check out some of the older books on cryptanalysis, which do talk about things like how to break a Caesar cipher. This is a little bit different because we're not, you know, rotating every A by a certain number. But all the same, we will, you know, be looking at it in a very similar fashion. All right, to catch up with Chad. Could someone willing to hide the cipher send a message that is all eyes and never reveal one single thing about the nature of the cipher to anyone? Well, yes, certainly. That's totally possible. I mean, there's nothing saying that if I were to send 256 eyes, you know, just the character I, to another person, there's no way to proof positive that I didn't send them something that was not encrypted, or that was encrypted. In fact, at that point, you know, because we're either sending a repeating pattern or we've sent a 256 byte message, we have one of two things. Either we're sending a pattern for some reason, that's kind of weird, or we used what's called a one-time pad, where we have the key is exactly the size of the input message. And one-time pads are the only type of encryption with perfect security. They're also not used because they are ridiculously inconvenient to actually use in practice. You can only use them once. You have to manage to keep the key secret as well as the clear text. It's a pain. But to your point, yes, you absolutely could come up with a key of exactly the size of the message that you wanted to send, and then XOR it so that you came up with just eyes, and then send that along. Of course, at that point, when you send the key, you're essentially sending the clear text anyway, but encryption ciphers used in practice are a lot more complicated than simple XOR and are hopefully designed so that the message can't reveal anything about the key. That is absolutely correct. One really, really good book that gives you insight into the way that people approach designing ciphers is a book called The Design of Rheindal. Rheindal is the name of the algorithm that's used for AES. So everything that powers TLS nowadays, that's going to be using Rheindal. The fact that there is a well-documented instance of the design of a very strong industry standard cipher is really great. It's, from an academic perspective, it's fantastic. And I would love to recommend to anybody who's interested in it, in the topic, like, read The Design of Rheindal. It's very good, and you can get it used nowadays for pretty cheap. All right, so let's go ahead and copy 5 to 6A. And our first step first real step is going to be writing a function to compute Hamming distance. So we know the difference between this is a test and Waka Waka is 37. Now this one, yeah, it feels like this belongs in strings. So again, just as a quick check to make sure that everything is working as expected, I'm just going to run, and everything is working as expected. In this test, we don't need XOR, so we'll just drop that out. Browser windows over the... Man, you know, some people just aren't very good at streaming. So let me catch you up on what I just did. All that I did was copy 5 over to 6A and did a bunch of data entry to make sure that things are working. I wrote our distance function just to return a constant 0 for now. And I ran the test to make sure that we're getting 0. So, obviously that's wrong. Let's figure out what we need to do to get it correct. All right. So probably the first thing that we could do here is just find out what the result of XORing those two is. So we've got a lot going on there, which is fair. Let's drop this to hex. And again, a lot going on there. So instead of to hex, let's give us bytes, and then we'll map it. Remember earlier, we saw that we were able to coerce a given number into a string, converting it from base to a base 2 number, just so that we get a nice representation. So we'll do a.2s for toString, and we'll just take a look at this in binary. So there's a lot of different ways that we could do this. I'm going to do this the quick and dirty way, the super duper quick and dirty way, which is, I am going to tell you right now, the bad way to do it. You shouldn't do it this way. There is a known algorithm that is efficient for computing Hamming distance. I'm not going to use it. Because right now, we already know exactly how to get at the data that we need in a way that we can kind of work with it, so... And I believe... All right, so count is not it. We do need to recourse it to that. Now, the nice thing about counting, I'll show you, is that we can pass count a function. So count by itself just counts how many things are in a given array. However, what we can do is say, can you tell me how many of these are even? And the answer is 2. How about how many of these are greater than 0? The answer is 3. How about how many of these are equal to the character 1? So this is all don't want to shadow the A and B that we passed in. So this is dirty and bad, and if this weren't for demonstrating that, hey, it's okay to approach these things and just do the hacky solution that works the first time until it stops working, I would encourage you not to use this solution. But again, what we care about is getting the answer 37, which hopefully we're about to get. There we go. So again, what we did here, we just said, hey, we're going to take the XOR of A and B. We're going to look at the raw bytes. And the raw bytes, you know, we had 3, 7, 2, 24, etc. Had all this. And then we said, okay, that's useful, but could you turn that into a bunch of binary representation strings? So we got all of this, and we know that we're just counting the 1 bits. So we joined it together, coerced it into each character, and then we just counted the number of characters that were equal to 1. So, kind of cheated, you know, or at least we used a solution that feels a little bit like maybe, wow, you should have done a little bit more work. But that's okay. It's okay to be lazy. There's always time later on to make something better. All right. So let's start with that logic. Let's go ahead and pull down that file as well. Cool. So we got a lot of stuff going on here. All right. So we're going to start working on our big problem. I'm going to go ahead and just steal some code here. Now, this is all base 64. So let's go ahead and let's make it raw data. believe it was from base 64, but let me double check. 264, do we not have from 64 yet? Neat. Well, let's fix that. In fact, it's quite likely that we don't even need to do that. We can probably just do 64. Just to make sure I am cool. It looks good enough to me. I'm going to believe that it's correct. And again, here we've got not really this is going to be roughly the pattern that we're going to use. So let's just pull this up. So in this case, we're going to have candidates. These are candidate key sizes. Let's follow what they said. We're going to do 2 to 40. We have our function to compute a Hamming distance. Now what we're going to do is I'm going to take that, each one of those key sizes, we're going to map it across a function, or we're going to map a function to it, where what we do is we take that key size and we take the first and the second key size worth of data. So we'll say string 0 key size. And this may as well be multi-line. So since I haven't used that before, let's give ourselves an array is 0 through 6, or 0 through 5. Now, if key size is 3, we do A, 0, key size. I'm going to get 012. And A, key size, we get 3, 4, 5. Likewise, if key size was 2, we did A to take the key size, then we gave ourselves another key size from that first boundary. We get 1, 2, then 2, 3. So the idea here is just we're taking chunks of a known size, known within the scope of a given run of the function, but not going to be known up until the point where it's executing. Now then, I believe that our function name was just distance, indeed. Now we're just going to give ourselves the distance between A and B. Now we can put those distances, and hopefully we're going to get right, yeah. Handy trick, by the way, you can have your script execute in IRB. which is quite nice. You can watch things happen step by step. But in this case, we just want to see that print happening. And we've got a bunch of distances. So that's good. So now we've got an edit distance. Next, we need to also normalize that result. We're going to divide by the key size. That way we're not biasing smaller key sizes. So, I'm going to go back here. And one thing that I'm going to do here is I'm going to coerce that key size to a float for this division. And the reason for that is pretty clear. Let's say I have the number 5 and I divide it by 2. And I'm going to take some t and I'm going to let people say what the correct response for Ruby to tell me the answer to this question is. If you've been through first grade, you probably know the correct answer, so... So yeah, obviously the answer is 2.5, and for the purpose of us comparing, it should be 2.5. But because we're working within the integer space, 2.5 doesn't exist, so we only get 2. If we change that 2 to a float, all of a sudden we're working in a context of floating point, basically numbers with decimal points in them. So now we get 2.5. That's going to matter because otherwise we're likely to get ties in our score that aren't really deserved. Now then, the final thing that we're going to do, well, let's make sure this works first. Yep, and you can see now we've got a bunch of different numbers. It looked like we had a bunch of stuff tied. Not quite as tied as it was previously. Now, one other thing to do here, though. Like, looking at these, I can kind of reason about them and guess, you know, well, that first entry is for 2, so then the next one must be 3, 4, 5, and so on. That sucks. Let's just give ourselves a tuple where we say score and key size. Now we can say 2.5 to 2, 2.0 to 3, 3.5 to 4, 1.2 to 5, and so on. So, great. Now I think that is time to update my instructions. All right, so our next step, key size with the smallest normalized edit distance, is most likely going to be the correct candidate. So what we should do is take the smallest 2 to 3 key size values, or we can take 4 key size blocks instead of 2, average the distances. For now, because I'm going to be lazy, let's just take the smallest 2 to 3 key size values, and then after, of course, sorting by the normalized edit distances. And we are going to follow the instructions from there. So we've got distances. Let's go ahead and sort them. So it looks like we are getting a pretty good sort. It looks like 5 is going to be pretty likely. 5 looks real promising. Ironically, 3 and 2 are the next 2 candidates, which are which sum to 5, but that's just a coincidence. But yeah, let's take a look at 5. Just looking at the list here, I noticed that 20 has a relatively low score as well. low being better in this case. I'm willing to bet that if I keep on looking, 15's probably real close. Yeah, 15's close to the top. I wonder where 10 is. I would expect 10 to be higher than 20, but let's work with just the first one for now. We're going to take the first entry there and the last entry of the first entry. Assign but unused. Go away. Please go away. There we go. So, because we've got a 2-tuple inside a list, we're taking the first entry in our sorted list, and then we're taking the last element, which is that 5. So, now we need a good way to break up this, this ciphertext into chunks of that length. Thankfully, we're working in a language that's vaguely functional. We have a really nice method available to us called each slice, which gives us slices of a known length. So if I were to say 0 through 9, and I knew that I want chunks of 2, let's say each slice 2, and I coerce it back into an array, you can see we've got 0, 1, 2, 3, 4, 5, and so on. So we're just going to make use of that each slice function, because it's super duper convenient. So we've done that. We've broken it up to blocks of key size length. Now next up, we need to transpose those blocks. I'm going to make a block that is the first byte of every block that is second byte of every block, and so on. So thankfully, again, we're working in a vaguely functional language, so this isn't too terrible. Because what we can do is 0 up to exclusive. Let me explain what that means real quick. So you've been seeing me use, let's say, 0 through 9 to get 0 through 9, 10 values in total. But we can have exclusive ranges as well that don't include the very final value. In this case, it's exactly what we want, because otherwise we'd, use parentheses and do arithmetic. Nobody likes that. Arithmetic is gross. So we've got 0 up to exclusively that candidate value. And so from here we can map that to is that right? Yeah, it's exactly right. Arithmetic's why we made computers, so we can avoid doing it. Jeff and Ubuntu, welcome in. All right, so actually what we're going to want to do here for these cipher chunks, and I apologize, I should be externalizing this just a little bit more. So ultimately, we've got chunks of 5, and we want to turn those into 5 chunks of a lot. So the first thing that comes to mind is, well, let's just take n bytes from them, or the nth byte from each. And actually, I think that we can do that. That's a good first pass. We'll see what that looks like. First, let's go ahead and make sure that things are still working the way that we think they are. definitely not. So on 20, I have screwed up. Right. So string, we need to break it up into... let's just go to chars. So we've got individual characters. Yep, that's a lot. Don't know what I expected. Probably should have been it. But I'm going to choose to believe that that is, in fact, the data structure that I'm looking for. So now we can do 0 through candidate. We'll map it to, and this is kind of gross. This is another one of those things that there are better ways to do, but I think that this is probably clear. And again, if it's oppressively slow, we can revisit it. But let's say cipher chunks. Now this is gross, and it really kind of hurts the eyes to read. So I'm going to explain exactly what this is. So we've got 2 maps going on here, which really sucks. But we can kind of visualize it on a smaller scale. So let's take 0, 1, and 2. And let's have first a array of a bunch of strings. Let's say they're going to be 4 large. So, hello stream friends. Broke it up into a bunch of individual characters, and now we've got slices of 4. We can see that if we coerce it to an array. We've got a bunch of slices of 4. That last one doesn't fit, which is going to be an interesting thing that we'll probably have to care about. So, next, we know that our candidate size for this is going to be 4. So now we're going to map, and we're going to take a function that itself is going to call another map specifically on that string array. Which means that we've got a function that's going for each one of these numbers into the string and executing across all of them. This is pretty dirty. There's a lot of iteration going on here, and there are cleaner ways to achieve this, but believe it or not, this is one of the simpler ways to look at it. Does this language have matrix functions or a library at all? Absolutely, Ruby does. I'm avoiding them. Because the more that I stick to the standard library and writing our own tools, the more I'm able to explain just in terms of, here's what we're doing within the language. So, what we get here is a bunch of strings, except everything except for that first one ends in a nil, which is gonna really suck when we try and join them all together. Oh, except it doesn't. Well, never mind. That's actually delightful. I figured that I was gonna have to give a crap about that, but turns out I don't. So, neat. And at this point, like, putting more stuff into that first nested map just really sucks. So we'll just eat the extra time to do one more iteration over. And there's our hunks. We'll go ahead and And let's this time only look at the first, let's say, 10 bytes of it, so that we don't blow up our scroll back again. So far, it looks like we're good. So we've transposed our blocks. So let's go ahead and move on to our next step. All right, so next we're just going to solve each block as if it was a single key XOR. So we already know how to do that. In fact, we can just steal the code that we wrote. All right. So here again, we're going to just map over that entire block of hunks. All right, and we can really use most of this code. I don't remember what A was meant to be. Let's double check. Aha, A is just A prime, which was some clear text, or non-encoded text. There we go. So we're going to trust our function. We're going to say, this is going to work. I'm choosing to believe it does. We're not going to be displaying anything here, so we're going to drop that. Yeah, we're going to drop that representation there because we don't need it. Now we know that we've got the first of the sorted tuples because we want our highest score. We'll take the last entry in that tuple. We'll just assign that real quick, and we will say print those scores. Just see what we've got here. And in theory, we have some keys. Looks suspicious in that we got a bunch of repeating characters. Let's double check. What is it? What are your secrets, friends? O-O-I-I-O. Interesting. We might have barked up the wrong tree. We'll find out real quick. But we already have multi-byte XOR code, so that will edit. We are taking the keys. Okay. And our original text was just called string. Cool. And for the sake of not flooding, let's just double check the first 20 bytes of the result. Oh. So I'm going to say that this is definitely not correct. All right, so just saying, hey, let's go with our first result every time and believe that everything is working correctly didn't quite work out. That's okay. These things do happen. So now that we're kind of pushed back a little bit to square one, as it were. Now we have to start thinking about other ways that we could attack this. So for one, we said, well, let's just assume that that first candidate is always correct. And instead of that, let's go ahead and let's take 5. Just to make sure that I am getting the data that I expect to be getting there. All right, so there's our candidate sizes. So 5, 3, 2, 13, and 11. And let's see, you know, maybe one of those is going to be correct. If not, then next up we'll walk back even a little bit further. It had the advice that, hey, maybe take 4 key size blocks instead of 2 and average those distances instead. If this works, we don't have to go that route, but if it doesn't work, maybe that's the next thing that we try. Decidability, welcome in. All right, so now our data types stop aligning a little bit because up until now we had... Okay, cool. So we didn't have anything called candidates yet, which is nice because we can wrap all of this in a humongous map. And again, this is kind of gross, and that's okay. What we care about is just iterating and seeing the results as they come. And we will, again, just take 20 bytes for each of these. Now this is going to take a little bit. This will take probably a solid minute. So I am now going to take a sip of tea, chat. I'm not going to take a sip of tea at all. And again, it looks like we are not where we want to be. We are not getting what we were hoping for. How's it going, EFE? Yeah, it's a real good shirt. I'm a big fan of No Starch. And yes, right now the Humble Bundle has some really good books, including Serious Cryptography, which I've read about half of. It's a solid book. Definitely one worth considering. All right, so we're not going to change, I think, this setup at this point. But we are going to take a step back in one of the earlier steps, it suggested maybe take 4 key size blocks instead of 2 and use that for our averaging. So let's just double that. Let's double it up. Let's see if we get a different result. Ultimately, we're not changing really the amount of computation that we're doing by any meaningful amount. So this will take about the same amount of time. While this runs, chat if you've got questions, thoughts about what's going on so far, things that you would like to see tried, let me know. All right, well, it looks like that second result is probably going to be our hit. So let's go ahead and drop our key. So it looks like the key that we detected was probably half as large as it needed to be, or half as large as what the code thinks is correct. But that's fine. That is the sort of thing that a human can look at and go, yeah, that repeating key that is identical twice, probably going to be half the size, and that's no problem. But in this case, as long as it decrypts the entire thing, we don't really care. Let's see, there's maybe some tweaking that we could do here. This would be a great data set for us to go ahead and start tweaking our rule set, just to bring the score of the correct key up and the score of that invalid key with, I see some graves in there, I see a bunch of braces and greater thans. I think that those are all symbols that probably don't need to exist, you know, or they don't need to be worth probably as many points as they are right now. So let's go ahead and alter our rules a little bit. Because up until this point, we're only rewarding, well, the most common characters in the English language and other characters and spaces. Maybe it's time to start saying, you know what? Graves. You can tell that I use an ergodox. There we go. You know what? Graves and various types of brackets. Maybe you're not terrible, but maybe you're worth -3 points. Oh, not enough yet. Which is interesting. You know what? In fact, let's make them worth less. They will discount 2 of the most common letters in the alphabet. Once this is solved, can we go over the best looking histogram? Absolutely we can. I found myself wondering if I've done something wrong. No. Interestingly, now we still end up with a similar, but not the same. But with none of the previously offending. There we go. And let's drop this to a reasonable value, especially since a bunch of those characters are likely to show up in English text under some, circumstances. Let's see, what else do we have in here? Do we already have equals? Do now. The null byte should almost certainly be negative 1000. The null byte is negative 1000. The bytes that we're modifying at this point are technically bytes that could show up in English text. I'm honestly quite curious why this is insufficient. Oh, hey, no, there's a null byte in there. What are you doing in there? That's really interesting. There are indeed 2 null bytes. This final entry should be hit absolutely last, because the way that we are doing the score here, we're doing rules.detect. If you're familiar with, well, here, for anybody who's not familiar with Ruby, let me give myself an array of numbers. Now, we would all agree that in an array of numbers between 0 and 6, we expect that there are 4 even numbers in this. However, if we do a.detect x.even, this is a select. In fact, I'll do a select first. So select, we get all of them back. Detect, we get the very first hit and nothing else. Now, in order to simplify things, actually, let's just coerce this to int. And now if we get nil, it doesn't matter. That should actually be identical functionally. Nope, I lied. Oh. No, that's right. I remember why I did it this way. As you can see, we hit this fall-through case where none of the other things match. Why am I calling last? Because I get a 2-tuple here between the key and the value. The thing that was matched and the score. Do I do infosec? Yes. And just to double check, we do in fact get the expected result with negative 1000. We don't. We just get a different value. Which makes me wonder if I'm doing something weird up top. Yeah, I think that it is indeed time to... Well, the problem is that in this case, the scores are generated independently. That's interesting. Yeah, that null byte is really bothering me now. You know what? We never need a null. That should at least change our results. And it doesn't. Yeah, we should never ever need anything that's outside of the printable range. Let's tweak these scores just a little bit. And I would expect to at least see things kind of shuffle around. We've got that one really stubborn result. I'm not sure. No, that's a different result. So at least that's changed. Okay. Well, for the sake of moving on, we did, and this is why we take, you know, in results just to double check. So we do know the key at this point. I just realized what the problem is, and it makes a lot of sense. We are... I lied, it doesn't make sense at all. All right. Okay, so for each possible distance, we're calculating a key. This is not ranked at all. That's the problem. Okay. This is actually not ranked by the keys with the XORs in them. Sometimes you're just real dumb. That's a fact of life. So now we have a more reasonable understanding. This is just by... This is sorted by edit distance. Edit distance normalized by the score. Or rather, the edit distance normalized by the key size. That's the order that this is in. This is, in fact, not ranked by the ciphertext that's resultant. So that's why. Which is why we have keys of vastly different sizes. You know, sometimes you look at a thing and it feels kind of weird, and you just have to remind yourself that you're actually not smart at all, which I think that we have proved in this case for me. All right. But hey, we've done this. All right, well, it's gonna yell at me about having broken out of that, which is fine. Let's go ahead and prove to ourselves that we have indeed solved the puzzle. And it looks like we have indeed. So then, I had a question earlier. Just wanted to address step 8 here. For each block, the single byte XOR key that produces the best looking histogram is the repeating XOR key byte for that block. And what that's saying is essentially really what we were just puzzling over a little bit inappropriately. So for each one of the chunks of data that we had, if our key size was 2, we took every even and every odd byte and we lumped those together, and then we would do the hunt on it to figure out what the correct XOR key was. So at that point, we would say that for the space of 1 byte, so from 1 to 255, and really at this point, because it's repeating keys, or we should have been doing 0 to 255. But for each of those, we were going to come up with a response, and that response is going to exist in, again, the 1 to 255 space. We know what we want that to exist in. We want it to exist realistically, you know, like X41 up through the printable alphabet, X61 up through the printable alphabet, so, and then, you know, potentially, you know, we're going to want a bunch of X20, which is space. We're going to want, you know, X30 up through X39, and then probably some punctuation in there as well that we're a little bit more, you know, ambivalent about. But that's what we would call the histogram that we're getting out of that. Just looking at the frequency of exactly what we have laid out on our rules. The frequency of these vowels, the Eto and Shurdlu, which is our most commonly used letters in the English language. You know, the frequency of A to Z otherwise, frequency of space, again, frequency of these unwanted characters. Fisune, I appreciate that. I take that as a hell of a compliment. I think that any workplace, any group of people should be filled with people who are excited to share to whatever they know. I think that the measure of a person is the mark that they make on the world, and the way you make your mark is by sharing the things you know, sharing the things you're excited about, letting other people have a chance to share the things that they know and they're excited about. So, yeah. But yeah, I think that we can move on. I'm going to take a sip of water this time, and I'm going to see if anybody has any last questions about challenge number 6 before we move on to challenge 7. You wonder how badly salting the input string with unprintable rubbish would protect from this attack. Well, it would protect from these rules. These rules are extremely naive. I could start writing other rules that would definitely, you know, once it starts detecting specific English words, like "the" is a great English word to detect. But not just that, but, you know, digraphs, 2 English letters that are frequently encountered together. So there's lists of them. I'm not going to list them off the top of my head because I'll get them wrong, but there are well-documented lists of here are the most common, you know, pairs of letters to see next to each other, most common triads of letters to see next to each other. We could make some very, very complex and sophisticated rules that would help to protect against, you know, throwing some nulls in at the beginning. But say 1 real character, then 10, ran 0 to 255. Well, I mean, yeah, that would potentially protect against a naive attack. And make no mistake, this is not a sophisticated attack that I've written. This is a very naive attack. The goal of something like this is less about, you know, turning somebody into a crack analyst that's going to figure out everything, you know, piece by piece, and more about really coming to learn the beginnings of how you would approach something like cryptanalysis. Fisune, I wouldn't have guessed that English isn't your first language. Yeah, I have very little patience for people who think that hoarding language is, or hoarding language, who think that hoarding knowledge is the way to go. I'm glad to hear that you've moved on to a better position than that. All right. Let's move on. Can certainly come back if people come up with questions later on, but at this point, if you've been following along, if you kind of understand what we went through there step by step, and this looks like something that's kind of fun, let me encourage you, like, seriously, go to cryptopals.com. It's completely free. You don't have to even sign up for anything. Start working through the challenges yourself, because if this seems fun and you've followed along so far, even a little bit, not, you know, understood and necessarily, like, come up with the right answer ahead of time, but just if it seems like it makes some sense and it seems interesting, go through these, because you've got hell of a future ahead of you, and there's a lot of value to be had going through stuff like this. All right, so after that we get what looks like a bit of a breather. We've got AES and ECB mode, so we'll be pulling down another file. It's been encrypted in AES 128 and ECB mode under the key Yellow Submarine. Yellow Submarine is exactly 16 characters, so that's nice. So we'll decrypt it. I'll just use the built-in, Ruby thankfully has a built-in OpenSSL library that I can use for that. It's just 7.text. Nifty. Yeah, so AES definitely can be tricky sometimes. And again, if you're interested in AES specifically, The Design of Rindal is such a good book. It gives you, like I said, insight into the process by which the algorithm itself was designed. It's a pretty short read. It's only like yay thick, which for a crypto book is pretty darn thin. And it's very, very followable. What's the book called again? Mr. Robot Shell. It is The Design of Rindal. And Rindal is spelled R-I-J-N-D-A-E-L. Because of course it is. We'll drop a link from the publisher in chat as well, just so you know what you're looking for. All right, so not doing it on stream or on, not doing it on capture because I'm reading off of my non-VM. I'm just pulling up the Ruby documentation for OpenSSL. which thankfully it has. It has an example for using CBC. For some reason, it doesn't give examples for using EBC, or ECB, excuse me. I wonder why. That's so weird. Never use ECB, by the way. Ever, ever, ever. It's not a good idea. All right, we will now copy... Probably copy 5 instead of 6 because 5 is simpler and we're not going to be using anything that we did in 6 for this. In fact, ironically, no, we're going to copy 4 to 7 because that's the closest that... We're going to copy 6 because I just realized that's, I think, all base 64 again. There we go. It was a ton of typing to avoid typing like 20 characters. All right, we are not going to need strings or XOR here. And let's go ahead and pull. What does ECB stand for? Good question. ECB stands for Electronic Codebook, and it has a really interesting property where if we give it, for, let's say, block size 16, if we give it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so null byte through hex 10, and it gives us back a solid block of 16 A's, just X41 all the way through. And then we give it that same block of 16, 0 through hex 10. It's going to give us back all A's again. It doesn't do anything to differentiate between individual blocks. So it's completely stateless, which, you know, is an interesting property. It is also extremely easy to analyze. ECB should never be found in the wild. Now, understand that when I say should, I mean invariably it will be, and you get to cry, but then you get to write kind of a friendly or sternly worded letter, whichever you prefer, to whoever's deploying ECB in production, assuming that it's not like a CTF that you're supposed to be owning, and tell them, hey, this is dangerous. You're putting your customers at risk. You're putting your users at risk. Whatever. Whoever's visiting it is being put at risk because ECB is trivial to analyze and break. All right. So we happen to know our key. It is just yellow submarine. Let's go ahead and indeed require. I think that we need to require a OpenSSL still. Yeah, we do. Please go away. There we go. All right. Just going to make sure that it doesn't blow up at me, because this is a relatively modern Ruby. I don't think that they've deprecated ECB and taken it out. Oh, hey, remember that time that I said we're not going to need XOR or strings? Remember that time that I was a huge liar? Yeah, no, it still exists. That's great. That's good. I mean, it's good for our purposes. It makes me kind of sad. And here I'm just, I'm walking through the documentation that's on the RubyDoc site, so I'm not doing anything particularly special here. Why is it not a good idea to use ECB? Because ECB, again, is stateless, which means that for every time that you send a given block of clear text at it, say yellow submarine, it's going to give you back the exact same ciphertext over and over and over again. And at the point where you can control the clear text, you can start gleaning insight into exactly what you're getting back. That's a little bit problematic at that point, because now, you know, you've got a situation where, hey, I've sent, you know, a bit of known text, say password equals, and I can move that around because I have an idea, you know, it's going to occur somewhere in this string. And then I can start using that to figure out, you know, what's the key. Any special reason for using Ruby? I've been doing Ruby since 2002. It's the language with which I have the most hours. Other languages that I tend to use on a regular basis are like Erlang and Haskell, which, while I enjoy coding in them very much, tend to be a little bit harder to follow along, and there would be a little bit more language level explanation. And my goal here is to explain more of the process and less of the language. There are some really fantastic Haskell streamers who are great at explaining the language alongside the process. But in this case, I want the focus to be, you know, in this case, the Cryptopals challenges that we're attacking. You know, at this point, the web flaw is old enough that I don't remember the details of it. Replay attacks were definitely part of the flaw, though. So, pack, one of those, I want to say that it's a Perlism. I don't know of a language prior to Perl. I didn't use any languages prior to Perl that gave us pack, at least where I used pack. Ruby's okay to understand. Just thought that I was using it for any special reason that makes things easy to do, the libs to be imported and stuff. No, for the most part, anything that we're using outside of like OpenSSL, I'm attempting to avoid leaning on any non-standard library functions. Anything that we're building, like you saw me pulling in strings and XOR, that's all stuff that we're building ourselves. I think that it's a lot more instructive and a lot more illustrative to show how we would go about building these tools ourselves. They certainly exist, but since the goal is, you know, gaining understanding, it makes more sense to build it yourself. All right, so here we have just walked through just some example code that's on RubyDoc. Hopefully it works. We'll see. Super duper not. Actually, pretty sure that we don't need do any packing there. Interesting. We're still reading 6. It's probably not going to be part of... That's not going to be helpful for us. Is that the same? 9026. Nope. 28 ECB. All right, well, our padding is definitely different. We didn't need to do any of the packing that was shown. And now, there we go. And hey, we've got more lyrics. Fisane, thank you very, very much for hanging out. All right, so this was really just let's make sure that we can do some decryption. Let's make sure that our OpenSSL libraries were working. Nothing really, mind-blowing or outrageous going on in challenge number 7. This is kind of like, the first couple of challenges where we were getting some foundational work laid so that we could move on and do cool stuff afterwards. So let's move on to the last challenge in this set. So we're going to have a file. We're going to say, in this file, there are a bunch of hex-encoded ciphertexts. One of them has been encoded with ECB, and we're going to detect it. So, and this is kind of what we were talking about before. It's telling us, remember that ECB is stateless and deterministic. The same 16-byte plain text block will always produce the same 16-byte ciphertext. So that's going to be the way that we detect which one of the ciphertext is encoded in ECB. I already have no wrap on? I think I do. Yeah. So each one of these lines is a ciphertext. One of these is going to be encoded in ECB. So the way that we're going to detect that, and they kind of give it away, the way that we'll want to detect it is hope that at some point on a 16-byte boundary, the same text in 2 different blocks was sent. At that point, we'll know with relative certainty that we're dealing with ECB. Right, so let's pull back here. And so this one is really just frequency analysis. There's not a lot that we care about. In fact, we don't need to do anything with OpenSSL. We just need our strings. And we want them broken up into lines, and we'll map it to remove the new line at the end of it. So now we've just got really just that file that we just read. In fact, what we should do is this. just to make sure that I haven't flubbed something here, we'll make sure that we've got an array of a bunch of unreadable text. That's what we expected. So at this one, really, all that we need to do is now we've mapped this. And again, we could inline these functions instead of calling map multiple times. We could compose these functions so that we don't iterate multiple times. But for the sake of clarity, let's go ahead and just kind of do this, you know, over and over again. My thought here is we are hoping that we have a repeated character pattern anywhere in this ciphertext, at which point we're going to have a duplicate block. And that duplicate block is a really good way for us to go, oh, that's probably a sign that this is done in ECB, because it's very, you know, unlikely to end up with duplicate blocks otherwise, especially in such short ciphertexts. Our expectation is that not only, you know, each individual byte having a relatively even histogram, you know, across all the possible values, but also entire blocks having a pretty even histogram for their values. And that at that point, you know, that's 16 bytes of information. Seeing two of the same 16 byte blocks, you know, in less than, what is it, 2 to the power of 8 is when we would expect to start maybe seeing collisions. And that's blocks, not bytes at that point. So that's a fair amount of data. And that was math off the top of my head, and it probably is wrong, but the bottom line is these are way too short for us to have repetition. So let's see if we can get some repetition discovered. And we're just going to use basic Ruby stuff here. We're going to, once again, break these up into characters, individual characters, and each slice of the block size, which is 16. And then we're going to join those characters back together. And just to show you what we're working with now, we've got just a bunch of strings with individual blocks in them. Now, this is another one of those things where in a lot of languages we would be writing this ourselves. However, there's a unique function that we have on array which does all the work for us. So we expect to have the same number across every single one of these arrays. Now, we happen to know that we're kind of hoping that we don't, but and we don't. So once we sort it, it kind of stands out like a sore thumb. We've got that 12. Which means that now we know that something's really weird here. So what we're going to do is we are going to say s.count and s get to go hand in hand. And for our sorting, we've got x and y. we're just going to sort it by that first element in that array that we've got. And the reason for that is that that's going to be our count. We'll do that first. And there is the ciphertext that we have pretty darn good certainty is going to be encoded with ECB. Because instead of 15 blocks once we've uniqued it, we actually only have 12 blocks. Challenge only calls for detection. Can we also decrypt this? Well, it's a good question. It would take a fair amount of analysis to even have a chance at decrypting something like this. However, again, if you are interested in this sort of thing, I will point out that set 2, which we're not going over tonight, we do start working on ways that we can attack both ECB and CBC. But, hey, we've got byte at a time ECB decryption. So there are ways that we can attack crypto systems. For a standalone ciphertext, that would take a pretty large amount of analysis. And realistically, we'd be able to guess at keys, but without really having a little bit of insight into what the clear text was, odds of us figuring out what that says without a ton of work are relatively small. But I want to encourage anyone who's interested in this topic, who, like I've said, if you've kind of followed along, even a little bit, even just kind of, sort of felt like you were hanging on and catching up, and this seems interesting, do these challenges. Start from set 1, work them out yourself. It's extremely instructive, and there's a lot of difference between, going through the motions and doing something yourself and, just following along with some written out instructions. I'd urge you, don't look up answers until you've finished a given set, or at least a given challenge. And at that point, start looking at other answers. Once you've solved it and you can say, hey, this is correct for sure, I'm confident of it, then tons of people have put their answers online. Go start looking at other people's solutions. You're going to get new ideas about how you could have approached it, because tons of people approach this sort of problem in very different ways. And there's only knowledge to be gained by going and looking at the way that other people approached it, kind of looking into it and going, what challenges would this approach have versus the approach that I took? What challenges that I had would this have sidestepped and made it so that I didn't have to worry about it? And just broadening your tool set bit by bit while you work through these sorts of things. It's a very, very rewarding process. I've been up through set 6. I need to go back and do the last sets. 7 is published. I think 8 is not yet completely published. It's not. So, but I need to go back and finish set 7 at minimum. But this is the sort of thing where if you're even a little bit interested, you've only got stuff you can only gain from doing stuff like this. So before I call it quits on this set of challenges, any last thoughts, any questions, anything from chat? My brain's nothing special. To respond to I wish I had your brain. My brain is absolutely nothing special. I've spent time, reading and tinkering and playing with stuff. I've done nothing that anyone else couldn't do. if I've had any advantage, it's just been that I've had some time that I can use to read up on tons of technical topics. But in this case, I had an early interest in math, and I had access when I was in grade school to a library that had books on, at the time it was just like Caesar ciphers, and it presented it as puzzles, but they were very fun, which definitely set me up for being very interested in this particular domain. But beyond that, there's really nothing special here. Anybody can do this. If you're interested in something like this, you are 100% capable of taking it on. Nasha, thank you very much for hanging out. I'm glad that you had fun. Have a wonderful evening. I feel like that's a good note to end on, actually. So yeah, I'm not going to be cutting stream, but we'll be shifting gears a little bit. But yeah, there's nothing special about anything that I do. Everybody is capable of it. And just one more time, if you're interested in this topic, there are a ton of books that are very, very good for it. One of them is literally just entitled Cryptanalysis. The Design of Rindal, which I've previously mentioned, is extremely good. Once you start reading through that, a lot of other attacks start really making sense. Serious Cryptography was previously mentioned by No Starch Press. No Starch really hasn't published anything that's bad. No Starch, everything that they touch turns to gold. They're great. Beyond that, honestly, this is one of the best resources that are around for learning certainly the basics of cryptanalysis and ways that you can attack ciphers. Turns out that most ciphers are broken in ways that have nothing to do with the math behind them. There are practical attacks against a lot, certainly of historical ciphers. And once you start, working through these, you start kind of understanding. The more that you build on this topic, the more everything else makes sense. But yeah, thanks for hanging out. Just one last time, anything that I've done here, if you're interested in it, I guarantee you're capable.